Hello and welcome back to Timberwolf Tutoring. Today we're going to be covering the topic of trigonometry, at least the intro to it. So trigonometry is, as the name might suggest, it has to do with triangles. It's a topic from Integrated 2 or Geometry, depending on what kind of math program you have. And it will come up in many of your future math classes as well, so having a good understanding of it is very important for math classes past the one you're taking. So let's go ahead and jump right into what trigonometry is. So an overview of this video, we're going to start by defining what the heck trigonometry is. Then we're going to look at the functions sine, cosine, and tangent, which are the three main trigonometry functions. Then we're going to look at our two special right triangles, which are the 30-60-90 triangle and the 45-45-90 triangle. These numbers are going to be the angles in our right triangle. Then finally we're going to look at some applications of trigonometry in the real world. So how you might use it in a career, whether it's science, architecture, or something else. And then we're going to find an example problem using one of these applications and calculate the height of Mount Everest. So let's jump right into defining trigonometry and the cosine, tangent, and sine functions. Alright, so we're going to start off by defining what is trigonometry. So to define that, we're going to take a look at these two right triangles right here. And what we can observe immediately is that both of them are right triangles, and both of them have an angle of 52 degrees. So we know that since these triangles share two angles in common, and therefore the third angle in common, that these two are similar triangles. And we can say that any triangle that's a right triangle with a 52 degree angle will be similar to both of these triangles, because if they have all three angles the same, they'll be similar. And what this means is that the ratio of the sides will be constant for any right triangle with 52 degree angle, because they will all be similar. So for instance, AB to BC is the same as A prime B prime to B prime C prime, regardless of how big or small both triangles are. And so we can say that all three of these ratios here are true, no matter how big or small the triangle is. And this is true for any right triangle with angle of 52 degrees. So this lets us say we have some triangle, and we don't know much about it, but we know that has an angle of 52 degrees. Well, just from that, given that it's a right triangle with 52 degree angle, we can automatically find these ratios by comparing it to a different triangle 50 degrees. And since these values are constant, we can express them using a function. So we say that the ratio AC to BC for the 52 degree angle triangle is going to be equal to sine of 52 degrees. And we can see that since 52 degrees is the angle ABC, AC is the side opposite to that, and BC is the hypotenuse. So sine is the opposite side to the angle over the hypotenuse. Similarly, if we want to find the ratio AB to BC in a right triangle with 52 degrees, we say that this is equal to cosine of 52 degrees. And cosine in this case is that side adjacent to the angle over the hypotenuse, so adjacent over hypotenuse. And lastly, if we want to look at the ratio between AC and AB, then we call this tangent of 52 degrees, tangent being opposite to the angle over adjacent to the angle. Now this is important because say we're given some random triangle with a 52 degree angle, and we're given one of the sides but not the other two, and we want to find the other two sides. Well, we can use these values sine of 52 degrees, cosine, and tangent of 52 degrees, and find the ratio between that side and the other two sides, just by knowing the 52 degree angle in a right triangle. And then, based on this, we can find those other two side lengths just from one side length on the angles. And you might be asking, well, how do we know what the value of sine of 52 degrees, cosine, tangent of 52 degrees are? We haven't defined how to calculate the values of these functions. Well, you can use your calculator for them. And there are a couple special cases that I'll talk about in a second, but for the most part, you're going to be needing to use your calculator for this. So now one other interesting property about sine and cosine in particular is that if you notice these 52 degree angle triangles, take a look at the angle BCA. That one is 38 degrees because the angles in a triangle have to sum to 180. So when we say that AC over BC is the sine of 52 degrees, we can also look at the other angle in the triangle, the 38 degree one. For that one, AC is adjacent and BC is still the hypotenuse. So that would be adjacent over hypotenuse for the 38 degree angle, or cosine of it. And similarly, if we want to do AB over BC, that would be opposite over adjacent relative to the 38 degree angle. So we'd have that be sine of 38 degrees. And in general, we can say that the sine of an angle in a right triangle is equal to the cosine of the other angle in the right triangle, and similarly cosine is the sine of the other angle. This is because the two angles have related opposite and adjacent sides, because if it's the opposite side for one angle, it's the adjacent for the other one, and vice versa. So now that we have a basic understanding of what these trig functions mean relative to a triangle, I'm going to show you a few special cases for two very special triangles and angles. Alright, let's take a look at these two triangles right here. These are our special right triangles. So if you look at the one on the left, triangle ABC, we can see that it has a right angle, obviously, since it's a right triangle. And then the two angles that we have are 60 degrees and 30 degrees. And you'll notice the side lengths labeled 1 and 2. Those are the lengths of the sides. So we know that the long side has length 2, which is given. But let's say we don't know the length of AB yet. And it turns out it will always be 1 if the hypotenuse is 2, but why is this? Well, to answer this question, what we'll do is we'll reflect the entire triangle across the line AC, and we get this, A prime, B prime, C prime. So now, if you look at this bigger triangle that goes from B to B prime and then to C, we can see that the top angle is equal to 60 degrees, the bottom angle being a reflection of that angle is also 60 degrees, and the angle on the side, since it's the sum of two 30-degree angles, is also 60 degrees. So since all three angles of this triangle are 60 degrees, it's an equilateral triangle. That means that since the hypotenuse BC was length 2, that's given, we know that B prime C prime will also be 2, and more importantly, B prime is going to be 2. Since AB is exactly half of BB prime, we know that it has to have length 1, just because it's exactly half of the side of length 2. So just by knowing that this original right triangle has angles 60 and 30 degrees, we can conclude that length AB is exactly half of the length BC. And then, using the Pythagorean theorem, we can then extrapolate that the length of AC will be root 3. And we can scale this triangle however we want. Because of similar triangles, we know that any right triangle with a 30 and 60 degree angle will have exactly these ratios. So, how does this help us? Well, we can go back to the original sine, cosine, tangent function we had previously, and we can say, what is the sine of 30 degrees? Well, since all 30-degree right triangles will have these ratios of sides, we can say the sine of 30 degrees will be the opposite side, which is 1, to the hypotenuse, which is 2, so the sine of 30 degrees will be 1/2. Similarly, the cosine of 30 degrees will be the adjacent side to 30 degrees, or root 3, over the hypotenuse, which is 2, so cosine of 30 degrees is root 3 over 2. And with a bit of work, we can find the rest of these trig ratios right here. Sine of 30 equals cosine of 60 equals 1/2, and the other ones. I leave it to you as an exercise to double check all these and make sure they're correct. But this is helpful because now, instead of using our calculator, whenever we're faced with the value sine of 30 or sine of 60 or any trig function of 30 or 60, we can immediately figure it out just from this one right triangle. So now let's take a look at the triangle on the right, DEF. This one's a bit more simple. It's an isosceles right triangle. So based on the fact that it's isosceles, we know that the two legs will be equal, and to simplify things, let's say they have length 1. We also know that the two interior angles will be equal, and therefore they must both be 45 degrees, since the angles in the triangle have to sum to 180. Using the Pythagorean theorem, we can tell that the hypotenuse must have a length of root 2, and therefore all right triangles with angles of 45 degrees will have these ratios between the legs and the hypotenuse. Each leg is always 1 over root 2 of the hypotenuse. The hypotenuse is root 2 times both the legs, and both the legs are equal. So based on that, we can find all the trig functions of a 45 degree angle. We can say that sine of 45 and cosine of 45 are both 1 over root 2, since for each 45 degree angle, the opposite or adjacent side will be 1, and the hypotenuse will be root 2. And that might not be exactly 1 in root 2, but every isosceles right triangle will just be some scale of this. So even if like the long side is, the hypotenuse is like 10 times root 2, then the legs will both be 10, so it always scales to be 1 over root 2. And tangent of 45 degrees, this is the easiest one to remember, is just 1, because both the legs will be the same in an isosceles right triangle. So now we have these 5 values. We have sine of 30, sine of 60, tangent of 30, tangent of 60, sine of 45, tangent of 45. I guess that's 6 values. And these are the most important values for sine, cosine, and tangent. So it would do you well to remember these 6 values. They're not super difficult to remember. If you ever forget them, you can just like draw your diagrams to figure it out. The 45-degree angle ones are easier to remember with diagrams because it's quite easy to figure out that an isosceles right triangle must have these properties. The 30 and 61 is a bit harder to remember, so it's more helpful to memorize those values. But I always say that it's never a good idea to just memorize something without knowing where it's coming from. So make sure you understand why these values are what they are before you just memorize them. So anyway, now that we know what trigonometry is, we know some special values of the 3 trig functions, now we're going to come see some examples of where trigonometry comes up in real life, and also do some practice problems based on these applications. So, let's jump right into it. Alright, let's take a look at some applications of this trigonometry you've been learning. So trigonometry has a lot of applications, despite how it may seem. Let's go ahead and go through a couple of them. So one of the most important ones is measuring the height of tall objects. And we'll see an example of this in a second, but let's continue. You also use it in architecture. It's very important because, like, say you want to put a roof on a building. You probably want to find the optimal angle of the roof so that it doesn't cave in, but it also looks nice. And additionally, you may need to find, like, how high up you need to lift something, or the angles in the house when making blueprints. It comes up a lot in architecture. Next, there's astronomy and space research exploration. This is back to measuring the height of tall objects, except instead of figuring out the height of something really tall, you're figuring out the distance from Earth to some celestial object. You can figure it out by finding the angle it makes with Earth and the Sun, and then comparing that with the distance from the Earth to the Sun, and using our trig functions to figure out how far away a distant object is. Also satellite systems. To keep a satellite in orbit, you need to do the math to figure out, like, how to keep its momentum well in comparison with the forces of gravity from both the Earth and the Sun, and occasionally the Moon, or wherever else you happen to be launching your spaceship. And trigonometry is vital in that. It's like, you have momentum going in multiple different directions, you need to figure out what angle your satellite is going to be going in based on those directions, or if you already know what angle it needs to be going at, you can figure out how fast it needs to be going in a direction. Physics and its applications, this is one of the more important ones. It's very simple. So you have an object moving at some speed horizontally and some speed vertically, usually due to gravity and a thrown object. Like, as a very simple example, say you fire a bullet. It's moving very fast forward and it's also dropping. And we want to figure out at what angle it's going to be moving at any given time. Well, we can look at the speeds as a triangle. So, like, if it's going 10 meters per second forward, we can show that as a triangle with length 10. If it's dropping at 100 meters per second, we can show that as the length being 100. And now that we know these two sides, we use trigonometry to find an angle. Sound engineering. This is one that's a bit counterintuitive, but at its core, sound is really just sine waves, which sine waves are graphs of the sine function. By taking a combination of graphs of the sine and cosine functions, you can get any sound. It takes a bit to understand this. If sound engineering is something you're interested in, I recommend looking into this at some point, but this is a more niche application. Video game coding. As I mentioned, since physics are something that trigonometry is vital for, a lot of video games have physics in them. Like any platforming type game, any realistic game that has jump mechanics, really any game where you're moving around and there are natural forces moving you. You need trigonometry to figure out, like, what angle, say, take Super Mario Bros. You need to figure out what angle Mario is going to be moving at when he jumps, and is running or isn't running. And then navigation. If you want to find the fastest route from point A to point B, you need to figure out, like, what the distance from A to B is along multiple separate routes. And again, if you want to find the distance on, like, a diagonal route, you're going to want to use trigonometry for that. Like, say you know the length of one of the sides, you know the angles from where you're going to where you need to be. Trigonometry is also important to, like, figure out your absolute position on the Earth by using the angle from, like, where you currently are to wherever your cell phone tower is. So yeah, these are a list of applications for trigonometry. This is by no means comprehensive. There are probably a lot more applications of trigonometry, but these are some of the ones that I thought of just on a ground level search. So now, given these many applications, I'm going to pick measuring the height of tall objects and do an example for that. So, example, height of Mount Everest. So today, the height of Mount Everest, we measure it using a device that someone put up on the summit. This is a really great way to measure it since the device is obviously always going to be on the summit since someone put it there. So until like an earthquake of some sort knocks it down, we can use that to easily measure the height of Mount Everest. It wasn't always that easy though, because someone had to actually scale the mountain to do that, and everyone knows how hard it is to scale Mount Everest. So in the past, people had to measure the height of Mount Everest using trigonometry. So as an example to see how this works, consider this diagram right here. We have a tree, and we, the observer, are at point P, and we are 60 meters away from the base of the tree at this point. So now we use a device called an inclinometer to find the angle to the top of the tree. This is an inclinometer right here. There are many different versions of it, but this is a cool handheld version. And that can tell us the angle from where we are to the top of the tree relative to the ground. And we're given that that's 42 degrees in this example. So now, based on the 60 meters and the 42 degrees, can we find how tall the tree is? Well, we want to find the ratio between HT, the side opposite to the angle, and PT, the side adjacent to the angle. So what we can use is tangent, which is opposite over adjacent. So we have that the tangent of 42 degrees is equal to the length we're looking for over 60 meters. So then if we multiply both sides by 60, we find that HT, our missing length, is equal to 60 times tan of 42 degrees. And then plugging this into our calculator, we find the height of the tree to be approximately 54 meters. So pretty tall tree. So now, say we want to find the height of Mount Everest using a similar method. Well, we can find our distance from the mountain relatively easily, just by walking there. And using the same inclinometer, we can find the angle to the top of the mountain. So that lets us calculate the height of Mount Everest without ever having to climb it. And this is how Everest was calculated in the past. Like, before someone had ever climbed the mountain, they probably wanted to know how tall it was, and if you can't measure how tall a mountain is without having climbed it in the first place, that's a problem. But using trigonometry, we can easily calculate the height of the mountain without having to do very much work. So that's one of the many applications of trigonometry. So that's all I have for you today. If you want to see more examples at some point, please contact us and let us know. Until the next time though, you can look at this reference for the height of Everest, how it was calculated in the past. But thank you for watching, and I hope you have a great day. If you want to contact us to ask us questions, more examples, anything like that, you can email us at support@timberwolftutoring.com, or you can reach us on Instagram at timberwolftutoring. Thank you for watching our videos, it means a lot to us, and have a great day. This is Robin signing out.